All right, and we're back with part 3. So just to recap the video and recap the parts of the ear, because you are going to have a quiz on it, want to make sure that you guys got it. So if you're looking at the diagram at the top, so the outer part right here, the part that you can see, we're going to call that the outer ear. Then the first place that the sound waves actually enter the ear is your ear canal. Then the first place that actually vibrates, which is a really key question, is going to be that eardrum. Now, the reason it's called an eardrum is because when you think of a drum, that thin layer that's at the top of the drum that vibrates that you hit, okay, that is just like what this is. It's a thin layer that vibrates. So you've got your eardrum, okay, and that vibrates. And then your 3 bones that you see right there, your first one is the hammer, the second one is the anvil, and then the third one is the stirrup. Remember, your ear has 3 bones, okay? Hammer, anvil, stirrup, hammer, anvil, stirrup, hammer, anvil, stirrup. Okay, then that stirrup, when it vibrates, it pushes on the cochlea. There's a snail in my Coke, remember? And there's 2 things inside the cochlea, the cilia and the liquid. When that cilia moves, because the liquid's vibrating, that is what creates your electrical signal. And that electrical signal is carried by the auditory nerve to your brain. Okay. What affects the speed of sound? There's 2 main things that affect the speed of sound, the temperature and the medium. So how hot the thing is traveling through and what exactly it's traveling through. So let's talk about the mediums first. So if we have a solid, a liquid, and a gas, sound is going to move at different speeds through each one. Well, the reason is because the distance between the atoms. So if you look at the gas, you would know, well, the gas has a large distance between the 2 versus the liquid is like a medium, and then the solid is like a teeny tiny space between the atoms. So for air, if all 3 of these samples were at 20 degrees Celsius, we have air, which is a gas, moves at 344 meters per second. We have water, which is our liquid, that moves at 14,000 meters per second, or 1,400 meters per second. And then we have steel, which is our solid, and it moves at 5,000 meters per second. So then sound always moves the fastest through a solid. Always goes fastest through a solid. Okay. Let's see. Oh, erase. So to further explain, I'm going to read this to you so that you can fill in your blanks, and then we'll recap. In order for the particles to vibrate in a wave, one particle must then hit the next particle in order to pass on the energy and continue the wave. There is not as much space between the particles in a solid, so the vibration wave would move faster. In a gas, there's a lot more space in between the particles, so it would take longer to hit the next one. So my thought to you is think about dominoes. If you have dominoes and they're really spaced out, like gas molecules, they're really spaced out, it's going to take longer for one domino to fall and hit the next one. But if you have a solid and they're like this and they're pushed down, then you've got so much less space for one atom or domino to vibrate and hit the next one. Okay, speed of sound in different temperatures. So remember, there's 2 things that impact the speed of sound, the temperature and the medium. So for temperature, I'm sure you're wondering why I have maple syrup at the top of your screen. I'll explain in just a minute. So if you are in a desert and it is 115 degrees Fahrenheit, sound will travel faster than if you are in the Arctic, which is like -20 degrees Fahrenheit. So why is that? Well, think about the atoms in those two places. You've got a really hot place and a really cold place. So hopefully your mind goes, hey, I know the really hot atoms are going to be moving faster than the really cold ones. Ding, ding, ding. Because that's the reason why. At higher temperatures, particles move faster. So if sound waves push against the already fast-moving particles, then it will quickly pass through and vibrate the next already fast-moving particle. So think about it this way. Here's my syrup. If you take that syrup out of the refrigerator and you pour it on your pancakes, how is it going to go? How's it move? It goes really slow. If you take that same syrup, nuke it in the microwave, and then pour it on your pancakes, how's it move? It moves quite fast. So why is that? The reason is because the atoms in the hot syrup straight from the microwave are moving faster than the cold ones. So it's able to move quicker. All right, stop and think questions. So what affects the speed of sound? There's two things. What would travel faster? Cold air? What would sound travel faster in? Cold air or warm air if the humidity was the same? Explain why. And then why would sound travel faster through, would sound travel faster through water or bricks? I want you to pause and try to answer these questions. At the very, very end, I'll go over the answers, but really, I just want you to check to see if your answers are right. Moving on. Okay, waves have same basic things in common, whether it's a transverse wave, like light, or a longitudinal wave, like sound. So you've got your wavelength, your crest, your amplitude, your trough. All waves have these things, including frequency. So frequency, remember, is the number of waves in a specific time. When we're talking about sound, that determines the pitch, okay? If you have a very, let's think about a pageant queen, okay? So if you have a pageant queen and she's waving nice and slow, a low frequency, chances are her voice is at a low pitch because she's calm and lower. But if she sees her mom and gets super excited, then she's like, hey mom, and it's a higher frequency, so it's a higher pitch. Get it? So your frequency of the wave determines the pitch. So those two things together, the next thing you need to know is that they're measured in hertz. And now here is my next trick to remember. I'm a softball player, right? So, or baseball, I love baseball too. If I frequently pitch, my arm's gonna hurt. Okay, now I actually want you to write that down on the side margin in your paper. I'll do it again. If I frequently pitch, my arm's gonna hurt. So I put the two words frequency and pitch together because frequency of the wave determines the pitch. And remember, pitch is how high or how low sound is. Okay, and both of those things are measured in hertz. So as you're looking at this wave, hopefully you notice that if this was a sound wave, which it is because it's measured in hertz, you'd hear a higher and higher pitch sound. So this could possibly be like, because it's getting higher and higher pitch, which means it's a higher and higher frequency. Okay, the Doppler effect. I will read this while you fill in your blanks. The Doppler effect is a change in the perceived pitch when the source of the noise is moving. So, in the next video, we will further discuss the Doppler effect.